All right, so day 3 here for power series. So what we're going to do today is practice a couple more of these things, and then we're going to go into what the derivatives and integrals look like, okay? Which isn't a lot, it's just one example, but the example takes a while because you have to do 3 different things. So we're going to find the interval of convergence. So interval of convergence of, and here's your series, n going from 0 to infinity of -1 to the n times x plus 1 to the n over 2 to the n. Now you'll notice this thing is centered at -1. Okay, so kind of take a note of that. I'll put it right here. Note c is equal to -1, right? Because it says x plus 1, so you got to take the opposite. So centered at -1. But we're going to have to find the interval of convergence. And in order to find the interval of convergence, we got to find the radius first, right? The radius of convergence. So again, I know this looks like an alternating series, and if I was just telling you, hey, prove to me whether this alternating series converges or diverges, then you would use an alternating series test. But we're trying to find an interval of convergence for this, okay, for this power series. So what we're going to do is, again, use your ratio test, okay? So limit as n approaches infinity of x plus 1 to the n plus 1 over 2 to the n plus 1. That's the a sub n plus 1, right? Times the reciprocal, so 2 to the n, x plus 1 to the n. Now again, just to show you guys the in-between step, so I don't lose anybody, we are going to kind of rewrite this, x plus 1 to the n times x plus 1 over 2 to the n times 2 times 2 to the n over x plus 1 to the n. And we'll be able to cancel stuff out. Okay, so I just kind of expanded it. You don't have to show this step. I usually just cancel out within, but you know, just to remind you, this is what it really means when you see the n plus 1 power, right? So the x to the n, x plus 1 to the n will cancel out, and the 2 to the n will cancel out. So what I'm left with is a limit as n approaches infinity of, remember, I like to write my x terms by themselves. So this will be x plus 1 over 2. And notice that all of my n terms are gone. Okay, they all got canceled out. So since n is the variable of choice, that means I get to take out x plus 1 over 2 from the problem. Okay, so x plus 1 over 2 goes out, and inside all that's left is a 1. And we know the limit of 1 is 1, right? So this is basically what I have, x plus 1 over 2. That's my answer. But in order for this to be convergent, it has to be less than 1, right? And if you're wondering, like, why do we always do less than 1? I think Irina asked me, why not greater than 1? They want us to find the interval of convergence, so therefore I have to prove convergence of something, right? So since I'm doing the ratio test, then in order to prove that the ratio test converges, it must be less than 1. If they wanted me to find the interval of divergence, which honestly I don't think I've ever done, I would make it greater than 1. Okay, and then I would figure out, you know, what is it at that point. But in our case, it's less than 1 because that proves convergence. Okay, now a lot of times people will say, oh, so R is 1. But no, if you look at the way this thing looks, it's supposed to look like this. X minus C less than R. Not X minus C over B less than R. It's not supposed to look like that. So what you're supposed to do is get this B value, factor it out, and then solve for it over here. So this problem will become the absolute value. I'm sorry, change the color here. This is going to become the absolute value, half the absolute value of x plus 1 less than 1. But I'm not supposed to have an a term over here, right? One of these. I'm not supposed to have that there. That's not the definition. The definition says it's just supposed to be a basic x minus or plus a number in an absolute value less than an r value. So what I'm going to do is multiply by 2. And I get this. The absolute value of x plus 1 is less than 2. That now looks like it should, right? It's only supposed to look like this. An absolute value, an expression inside, less than some number. Right? R is supposed to be some number n, as they said, right? Greater than 0. So here we go. I have now found that my center is -1 and my radius is 2. Okay? So if my center is -1 and my radius is 2, what's my interval of convergence? -3 to 1. And there you go. Huh? So remember, you can think of it like a number line, right? So if I'm centered at -1, here's -1. So -2, -3, -4, and then 0, 1, 2, 3. I'm going to put a dot at -1 and then pretend to draw a circle with the radius of 2. So it would look like this, right? So it touches the -3 and it touches the +1. Interval of convergence. It's just an abbreviation. Interval of convergence. So there you go. Now, if they wanted you to figure out what are the endpoint, what are the endpoint convergence for these things? Like, does it converge at -3? Does it converge at 1? Then we'll do that. So let's practice that one more time because we've only done that once. So test for endpoint convergence. So remember, to test for endpoint convergence, you're going to say let x equal -3 and you'll let x equal to 1. And you're going to put them into your original equation. Okay? So our original series. So here we go. The sum as n goes from 0 to infinity of -1 to the n. Now remember, it's x plus 1 to the n, right? So it's going to be -3 plus 1 to the n over 2 to the n. And I'll write the other one since we're here right now. So this is going to be the sum as n goes from 0 to infinity of -1 to the n. X plus 1, so that'd be 1 plus 1 to the n over 2 to the n. But we'll start with the left side first. So let's simplify. This is the sum as n goes from 0 to infinity of -1 to the n, -2 to the n, over 2 to the n. Now here's a little trick. If you notice that you have a number that's negative taken to the nth power, you can actually split this into the following. -1 to the n, 2 to the n, over 2 to the n. You guys see that? Because -2 is just -1 times 2. So -2 to the n is the same as -1 to the n times 2 to the n. Right? It's just an algebra definition. The one that says ab to the n is the same as a to the n, b to the n. Right? So -2 is just -1 times 2. So old school algebra 1 stuff. Right? So what's -1 to the n times -1 to the n? It's just 1, right? It's 1 to the n. And what's 1 to the n? It's 1. So in other words, see you later. You don't matter. And 2 to the n over 2 to the n? That's just 1. So here is my sequence, or my series. Does that converge or diverge? Say again? Diverges, because if I try the nth term test for divergence, what's the limit of 1? It's 1. And what is it not supposed to be for the test for divergence? As long as it's not 0, right? That limit is 1. So by the nth term test, this diverges. So that means at -3, it should stay an open parenthesis. Okay? What about the other side? Well, let's simplify. This is -1 to the n, 2 to the n over 2 to the n. And we know the 2 to the n's will cancel. So I basically have an alternating series, right? Times 1, right? So does this qualify for the alternating series test? Does it converge? So you try the first test, which says the limit as n approaches infinity of 1 has to equal 0. Is this true? No, it does not, right? So this also diverges by alternating series test. So that means that you did all this work to find out that you were right in the first place. -3 to 1 is your interval of convergence. Completely, okay, found your interval of convergence. You know it doesn't converge at -3. You know it doesn't converge at 1. So therefore, you found out that that's the way it should be. It's not supposed to be like a bracket on the left or a bracket on the right or anything like that. It's supposed to remain like that. So this is your IOC. So we did one yesterday. We're doing one today just to kind of get a little bit more practice on what you do to find endpoint convergence. Notice it's not like terribly difficult to do it. You just got to be careful not to mess up on your addition and subtraction stuff or canceling out the right things, maybe factoring something out like we did over here on this side with the -1 to the n times -1 to the n, realizing like, hey, you put those together, it's really a 1 to the n, which really means 1, right? It doesn't matter how many powers you put to that 1, it's going to be a 1. Questions on that one? So what we did when we got to this point, we were done. According to the problem, they just wanted us to find the IOC. There you go. But normally they're going to say, when you find the IOC, always check the endpoints. Because if, let's say at -3, the series would have converged, then you were going to have to do this. To say -3 is included because it does converge there. If it would have converged at 1 as well, then you would have to kind of do that too. So the interval could change based on the endpoints, whether or not they converge. We tested them, and unfortunately for us, they both diverged. So that means we did a bunch of work for no reason. If I would have just stopped initially and forgot to do it, I would have still been right. But if one of those would have converged, so yesterday I think one of the sides did converge, then we have to make sure we include it. So yeah, the parenthesis means that it diverged at that point. The closed bracket means that it did converge at that point. So, all right, let me see. I'm just checking something here. So let's do one more of these things, and then we will get to the derivative part, okay? So this is example number 7. And this one's a little bit easier, I hope. It looks like it's going to be easier. So find the interval of convergence for the sum as n goes from 0 to infinity. Actually, it's supposed to be 1. I'm sorry. 1 to infinity of x to the n over n squared. So again, I'm just going to use the ratio test. Now, if both of these things had an nth power, then I would have used a root testing instead, okay? But in this case, one of them is n squared, so taking the nth root of n squared isn't going to help me, okay? But I can do the ratio test. So again, ratio test usually works. So if you don't know what else to do, just try the ratio test. So we're going to put x to the n plus 1 over n plus 1 squared times n squared over x to the n as our ratio test. Again, just to kind of make sure that I'm not losing anybody, I'm probably going to stop doing this from now on, but I'll do it one more time here. X to the n times x over n plus 1 to the n, squared, times n squared over x to the n. So you'll notice you can cancel out your x to the n's. And that's pretty much all you can cancel out. So limit as n approaches infinity of x times n squared over n plus 1 squared. It's a big squared. Now remember, I split up my x variables because I know I can take those out. Okay, any constants or variables can be removed. So I'm going to take out that x. I'm going to have an absolute value of x times the limit as n approaches infinity of n squared over n plus 1 squared. Now, if you look at the original series, the one in blue, you'll notice that's centered at 0, right? So kind of remember that because we're going to need to write that down later. What's the limit of that function right there? It's also 1, right? So then this is basically just absolute value of x. Right? And in order for this to converge, the absolute value of x must be less than 1. Notice the center is still 0. Right? Absolute value of x minus 0. That's what it is. So the center doesn't change. Okay? So that means my center is 0. My radius is 1. So what's my interval of convergence so far? If I'm centered at 0, but I have a radius of 1, so I go 1 to the left, 1 to the right, -1 to +1. Okay? So that's all. In this example, that's all they want you to do. But you know what? Let's find endpoint convergence. Like every time I've ever done an IOC problem, I always find endpoint convergence, even if they don't ask me. Because usually that's what they mean. Like figure everything out. We want to know what's happening on the left side, what's happening on the right. So from now on, unless they strictly tell you don't worry about finding endpoint convergence, always find endpoint convergence for these problems. Okay, so let's find endpoint convergence. We're going to let x equal to -1, and we'll let x equal to 1. Hopefully we don't waste our time doing this. So here we go. The sum as n goes from 1 to infinity. It was x to the n over n squared. So -1 to the n over n squared. And then the other one, n goes from 1 to infinity. It's 1 to the n over n squared. Now the left side's kind of easy, right? Just use the alternating series test. So part A, is it true that the limit as n approaches infinity of 1 over n squared equals 0? Yes, that's a yes, right? Is it true that 1 over n plus 1 squared is less than or equal to 1 over n squared? What do you think? Which denominator is bigger? Left or right? Left. So when it's a fraction, that means it must be smaller. So then this converges, right? by alternating series test. So notice I'm going to go back up here and I'm going to put a bracket on -1. Now let's check 1. This basically simplifies to the sum as n goes from 1 to infinity of 1 over n squared. What test can I use to prove this? P series. Well, P is equal to 2, so what does that mean? Does it converge or does it diverge? It converges as P is greater than 1. Right? So then I'm going to go back to the IOC and I'm going to put a bracket on that side. And here's my answer for that problem. So this kind of gives you a little bit more of an idea of why we did it. Because when we just did it the previous time, it looks like we just wasted our time. But now you see like, oh, this one actually does converge on its endpoints, so let's make sure we include them. Okay? So that's it for power series and endpoints in a sense, like normal ones, but they do want us to show you how you can take derivatives and integrals of these power series. Okay, so let me kind of show you what it's going to look like. So I'll put right here derivatives. And integrals of power series. So the reason why they're going to do that is because they're going to want you to see that you can take derivatives and integrals and still test for what they want you to test. Okay. One thing you'll notice is that the interval of convergence usually doesn't change between derivatives and integrals of the original power series. So in other words, if the original power series had a interval of convergence of -3 to 3, its derivative will too, and its integral will too. The only thing that's different is the endpoints may not converge in the same manner. So maybe a power series will have an interval of convergence from -1 to 1 with brackets on both ends, but maybe the derivative will have parentheses on both ends. Still the same interval, but maybe it doesn't include it on both corners. And the integral may include one, but not the other, right? So just understand that the interval of convergence for a power series, when you take their derivative and their integrals, will not change, but the endpoint convergence may change, okay? But the interval will stay the same. So let me see. I'm trying to read through this thing. That way I don't have to write as much for you guys. So radius of convergence is consistent. Interval, endpoints may change. So yeah, okay. So here we go. Given a power series. Okay, so we're going to call it a power series f of x, which looks like this. And it goes from 0 to infinity of a sub n x minus c to the n. Okay, so given that power series, then f prime of x. Okay, so notice how we started from 0 to infinity. Let me actually write this a little lower. I'm going to write the same thing, don't worry. But then f prime of x is equal to, note the starting position. Okay, the reason why they change it is because the first term will usually go away. So they're like, well, the 0th term is gone when you take a derivative, right? Usually your constant disappears when you take a derivative. It becomes 0. So they're saying, well, there's no sense in starting from the 0th term. It doesn't exist. So let's start from the first, right? So we're going to have 1 to infinity. And then it's going to be basically like what we did with our power rule. You're going to take the power down. So it's going to be n times a sub n x minus c to the n minus 1. So that's what it's going to look like. That's your derivative. So just take the power down and subtract 1. So that's our normal general power rule. And if you're wondering, why didn't anything change with a sub n? Remember, we're taking derivatives of x's, right? So our x terms. So that's why the power changes in the expression that has an x in it. A sub n is just a constant, so we just kind of leave it in front. We're going to have the integral of f of x dx equal to c plus, notice they include the constant of integration, n equals 0 to infinity, and then it's going to be a sub n x minus c to the n plus 1 over n plus 1. I guess I don't have to put the parentheses around that little piece. But it's just like what we used to do with integration, right? If you have to integrate x to the n, you write x to the n plus 1 over n plus 1 plus c, right? They just put the c in the front here, but it doesn't really matter. But I think they do it because they don't want you to get confused with maybe should it be included in the series or is it outside the series? So they're trying to tell you it's on the outside of the series. Okay, so that's how you take a derivative and an integral. So let's do this one last example, and then I think we're done. Let me see. I'm just checking something real quick. Yeah. Now this is a decent sized example, okay? So example number 8. And the reason why it's a decent sized example is because we're going to do the power series for it, and then I want you to find the integral and the derivative and check for the intervals of convergence. So it does require a lot of work, okay? So given f of x equal to the sum as n goes from 1 to infinity of x to the n over n, okay? So given that, find, so A, oh, I'm sorry, I forgot. Find the IOC, the interval of convergence for, and then A, we're going to, let's just find the original one first, f of x. And then we'll do the integral, and then we'll do the derivative. So this is why this problem takes a while. Okay, it's not because, oh my gosh, it's so hard to do, but we're going to do this thing 3 different times. And then checking the endpoints 3 different times. That means we're going to check endpoints a total of 6 times. Okay, and we're going to find an interval of convergence how many times? How many times am I going to find the IOC? 3? Not 3. Not 4. Once. Because didn't I just tell you? The IOC will never change. Whether it's original, derivative, or integral, it will stay the same. But I do have to check the endpoints, right? So don't waste your time finding the IOC 3 times, because you're going to notice it's going to be the same every single time. Okay? So I want to tell you that now. But we do have to check the endpoints. So we will do that 6 total times. But the IOC just once. So always start with the original function, because usually the easiest one to do. Okay, so let's start with the original function. Okay, starting with A. So I have this function here, and I'm going to have to check for its radius of convergence, interval of convergence, etc. So let's just do the limit as n approaches infinity of x to the n plus 1 over n plus 1 times n over x to the n. Now again, I'm going to cancel this stuff quicker now, okay? The x to the n will cancel with that x to the n, but that plus 1 part is still there. So this is limit as n goes to infinity of x times n over n plus 1. Well, that's an absolute value of x times the limit as n approaches infinity of n over n plus 1. What's my answer for this? 1, so it's just absolute value of x. In order to prove convergence, it must be less than 1. Right? So what's my center? 0. And my radius? So C equals 0. R equals 1. What's my IOC? Negative 1, 2, 1. Like this so far. Okay? And that's going to be the same IOC for the integral, the same IOC for the derivative. So I don't have to do any of what I just did. I don't have to do it again. Okay? It's already set. But I got to check the endpoint. So let x equal to negative 1. Let x equal to positive 1. So using my original function, n goes from, it was 1, right? 1 to infinity. 1 to infinity of x to the n over n, right? So if x is negative 1, it's negative 1 to the n over n. Alternating series test, is it going to converge or diverge? Let's see. A says limit as n goes to infinity of 1 over n should be 0. That checks. 1 over n plus 1 should be less than or equal to 1 over n. Also checks. So that converges. So let me write a bracket on negative 1. Now let's try again. N goes from 1 to infinity of, if x is 1, it's 1 to the n over n. What's 1 to the nth? That's just 1. So yeah, this is a harmonic, right? And what does a harmonic series do? It always diverges. So there's my interval of convergence for part A. Now let's figure it out for part B, the integral. Okay? We're going to integrate. So let me write part B here. Now we have to integrate the function. Okay? We have to integrate the function. I'm going to put it over here on the side. This is what we have. X to the n over n. Okay? So only the x terms. So that means that the integral that I have here is going to be, I'm just trying to write this out here for us. The integral is going to be integral f of x dx is, n goes from 2 actually, right? I should go up 1 to infinity. I forgot to put the plus c. I'll do that right now. Of x to the n plus 1 over n times n plus 1. Now, if you're wondering why did the n not become an n plus 1, it's because the n itself is not an x function. It's just an n value. So the n plus 1 came from that power that belonged to the x function. Okay? And then again, plus c. Okay? So there's my function. Okay? We're kind of focusing just right here. Now, the interval of convergence, we know, is from negative 1 to 1. Okay? But now I got to check the endpoints. All right? I'm going to have to check the endpoints from this thing. So, if I try negative 1, this is what I get. The sum as n goes from 2 to infinity of negative 1 to the n plus 1 over n times n plus 1. Okay, this is an alternating series, right? So does it pass part A? Limit as n approaches infinity of 1 over n times n plus 1. Is that 0? Yeah, so good. Does it pass part B? 1 over n plus 1 times n plus 2 has to be less than or equal to 1 over n times n plus 1. Yes. So, converges. So I'm going to include that. Now let's check 1. Okay, so the sum as n goes from 2 to infinity of 1 to the n plus 1 over n times n plus 1. Notice this is not alternating. This is basically this function right here. Now, if it helps, let me write it like this. How do I test this one? Huh? Direct comparison, right? I have a function 1 over n squared plus n. Let me check it with 1 over n squared. Okay? I'm going to check it with that. Now, which function is the bigger function? Yeah, so this is my b sub n. This is my a sub n then, okay? B is bigger, right? That's the bigger function. So if 1 over n squared is my bigger function, then I got to prove convergence. And if I prove convergence, that proves that a must converge. Does 1 over n squared converge? Yeah, by what test? P series, right? P is greater than 1, right? So since this converges by P series, then this converges by direct comparison. So what do I do with that positive 1 on the interval of convergence? I put a bracket over it. By the way, I know that this matches the other answer. That doesn't always happen, okay? So don't just assume that they're all going to look the same. Sometimes it's just chance. So there you go. So what about the derivative? This is why this problem takes forever, because I basically give us 3 problems in one, okay? They won't make you do this in an FRQ all 3 steps. They might say, here's your original, figure out the interval of convergence for your integral only. So then you're going to have to find your radius of convergence, interval of convergence, and test. But yeah, they're never going to make you do all 3. Unless, if they do, this may be the whole question, because this will take you a good amount of time. So we get out 31, right? So I'm going to work really quick with C, okay? And just watch the video. But the derivative for this, what would the derivative look like? Let's see. It's the function is x to the n over n, right? So it's going to be n times x to the n minus 1 over n. Oh, wait, you know what? I just realized something. The derivative should be at 2. I'm sorry. The integral should stay where it was. I just realized I did that wrong. I apologize for that. This should stay exactly where it was. I thought for some reason in my head, I thought I was doing the derivative. I don't know why. So this should stay at 1. So the integral should start at 1. The derivative, you always eliminate 1, so you have to start 1 higher. Yeah, so that you should be at 2. Notice these are going to cancel, right? So I have this. X to the n minus 1. That's it. That's my derivative. I know the IOC is from -1 to 1. But let's just see if it converges on both. So let x equal to -1. So n goes from 2 to infinity of -1 to the n minus 1. I'm going to have to use an alternating series test. Is it going to pass part A? No. This diverges by AST. So it's going to stay open on the left. What about if I let x equal 1? Well, this becomes a 1 to the n minus 1, which is essentially Just 1. Does that converge or diverge? By what test? By the nth term test. Okay, diverges by nth term. So, thankfully, we're done.